So first of all, I would like to thank Thomas for organizing the conference in this wonderfully stimulating place. Also thank you for having me here today. As the title of my talk suggests, I would like to address the issue of coherence states for generalized uncertainty relations. In particular, in the framework of Tsallis thermostatistics. So in particular, I would like to emphasize the role that Tsallis entropy plays in this business, and I would like to also show some particular implication that this can have. This work was done jointly with people from Salerno University, Gaetano Mobiase, Gaetano Luciano Petruzio. So actually, outline of my talk has 3 points. In the first part, I would like to mention what the generalized uncertainty relations are, and I would like to also mention one important conceptual tool I will use, and the tool is named coherence space, and I will generalize them, or GUP, for generalized uncertainty relations. In the second part, I will show how the Tsallis entropy will enter into the game, and I will rederive the generalized uncertainty relations into entropies. So I will get quantum mechanical entropic uncertainty relations. And in the last part, I will basically apply this scenario into universe cosmology by utilizing Linde's entropic gravity in this Tsallis modified form. So it is rather well recognized by now that general relativity and quantum mechanics, if they should join together somehow, they require some really fundamental conceptual shift in our understanding of the space-time. Recently there was again a revived idea that space-time perhaps should be discrete, coarse-grained on the Planckian distances. This is supported by various quantum gravity scenarios, starting from loop quantum gravity and ending with Wolfram cosmic solar automata. All of them more or less assume that the discrete structure at this length scale should appear. So of course, natural question which one might pose in the quantum mechanical framework. If you know that we have fundamental length scale, how Heisenberg uncertainty relation will be modified by knowing that there is yet another length scale apart from the fundamental length scale we already have, which quantifies the scale of quantum fluctuations. So actually, uncertainty relation should reflect existence of 2 fundamental length scales somehow. There are actually various ways how it can be done. They typically go under the name generalized uncertainty principles. The one which I will actually use here most is one of the simplest ones. It's actually also a toy model example of generalized uncertainty principle. It's this one, and the modification is minimal on the right-hand side, and you basically introduce just modification that is proportional to the variance or uncertainty in momentum square. And of course, evidently, when beta would go to 0, you have no modification, and when the beta is non-zero, then you would expect some modifications. But of course, it will be important that the momentum will be of order of Planck mass square. No, momentum of order of Planck mass. So actually, this inequality it's not something that is completely falling down out of the sky, but it is actually implied both various quantum gravity models, but it's also implied string theory, and I will also mention it's implied also by condensed matter models. It's actually something you can see even as an effective uncertainty relation in many condensed matter systems and nominal quantum optical systems. So, in fact, this uncertainty relation is very qualitatively different behavior than conventional uncertainty relation, in a sense that, for example, if you draw the diagram dp versus dx, you find out that there is irreducible minimal uncertainty in position. So we cannot go to 0. It basically implies that we have discretized space-time structure, space structure. If the beta is positive, this is what happens. If the beta, on the contrary, is negative, then you get maximum uncertainty in the momentum fluctuation, which is done by the fact that left-hand side of uncertainty relation must be positive. So right-hand side must be positive, and right-hand side be positive only for negative beta if you have some maximal value of uncertainty in momentum, which will be the case. I will be mostly concentrating here. In addition, the delta which I mentioned not necessarily need to be variance. It can be, for example, the Angenauigkeit in the sense of Heisenberg, it can be whatever. It can be expectation value of the modules of the operators rather than variance. But if you identify delta with the standard deviation, as we typically do in quantum mechanics, then that generalized uncertainty relation might be derived conventionally from this generalized commutation relation via the standard strategy invented by Schrödinger and Robertson, which is typically in textbooks, which is based on Schwarz inequality. In fact, this typically serves as a laboratory, a toy model laboratory for many systems in condensed matter theory and nonlinear optics. It's interesting that it's typically effective commutation relation, which appears even if you have system with constraints. If you constrain dynamical quantization, which appear frequently in condensed matter theory, when electrons, for example, moving on the surface of the Fermi hyperplane, which is typically true in very low temperatures. Then you have constrained dynamical systems, you have second-class constraints, so you must work with direct brackets. If you promote direct brackets into quantum theory, then you get commutation relations that have this non-trivial Lagrange size. So it's something that is really happening. We don't need to go to Planck scales. You can have another effective quantity that plays effectively the role of Planck mass. So another tool which I will use apart from GUP generalized uncertainty principles are coherent states. There are many definitions of coherent states, but the one I will use is the state that saturates Heisenberg uncertainty relation, or saturates uncertainty relation. So in its nutshell, coherent states are such quantum states in which position and momenta are as good localized as quantum mechanics allows. So they are most classical in a sense. So coherent states most closely approximate classical motion of particle, but at the same time they are most robust with respect to decoherence. So they decohere last. It takes longest for coherent state to decohere. So they are really wonderful tools for discussing quasi-classical limit. I mean, the passage of transition from classical to quantum realm. And that's the reason why they are so much used in quantum information theory and quantum optics, because of this robustness. Because they can allow to discuss the transition from quantum to classical realm. They are wonderful for discussing such strange concepts as a Schrödinger cut or entanglement, precisely to see how those concepts are disappearing when you go to classical limit. In this context, it's of course very natural hence to ask, how would look coherent states for generalized uncertainty principles? So in other words, if I would like to see how looks the semi-classical regime of GUP-driven universe, I would want to see how look explicitly coherent states that will describe that regime. And actually, it's not very difficult to construct such coherent states. You can basically follow standard textbooks like Messiah. You know that you are using Schwarz inequality, so you saturate Schwarz inequality when state P psi is equal up to constant, proportional to state X psi. And in addition, you kill this unwanted anti-commutator on the right-hand side by setting it to 0. So first is the saturation of Cauchy-Schwarz inequality. Second one is to getting rid of this Robertson term, which then automatically implies that this C must be pure imaginary number, domain 0. So basically, you get equation from here, and from here follows that the coherent state must satisfy this equation. Now, this equation is abstract in arbitrary representation, and you can choose representation you want to work with. And naturally would be chosen to work with position representation. However, in position representation, it's very difficult to represent in local operators the generalized commutation relations. It's much more convenient to work in momentum representation, because in momentum representation, the position operator is basically linear operator. It's local. While if I would go to position, the momentum operator would be non-local. This is anti-commutator, so it's how it is written is automatically symmetric operator. It might be shown, and we show it here that it's actually self-adjoint. With appropriate choice of the domain of definition, it's self-adjoint operator, which is real continuous spectrum. So you can now rewrite this equation for coherent state in momentum representation, just ordinary differential equation, which is as a solution, a function that is polynomial. This polynomial function has normalization factor, which of course for positive beta has this value, for negative beta has this value. If beta goes to 0, which means no deformation, then I get just conventional Glauber coherent state, which is the Gaussian wave packet, which we know is coherent state for Heisenberg uncertainty relation. So here I have Glauber coherent state for harmonic oscillator. So now, in order to understand a little bit more the structure of the coherent state, it's convenient to go from parameters beta and gamma to new two parameters, or reparameterize the original coherent state, and introduce new parameter q and b. I mean, it can be shown that this q, it's a monotonically increasing function of this beta, and when beta is 0, no deformation, q is 1, and when beta goes to negative values, q goes to values smaller than 1. In those new parameters, corresponding coherent state is this structure, which people who know a little bit statistical physics, the contemporary statistical physics, can immediately recognize as a transitional, as a probability amplitude for Tsallis distribution. Tsallis distribution is the subject, which is now extremely popular in complex, not in complex, but complex dynamical systems and statistical physics of systems with long-range interactions and correlations. So now we obtain probability amplitude, which is Tsallis type. Corresponding probability distribution has power rather than exponential law behavior. If we would now to keep two observables, which is typical case for coherent states like variance and mean, then Pauli type of distributions are not actually in accord with the conventional maximal entropy prescription, which tells you that I should get the typical state or probability distribution by extremizing entropy. So if I would take Shannon entropy and extremize it with respect to those two constraints, I would never get Pauli type of behavior. However, what I get standard Gaussian distribution, which is coherent state for conventional Heisenberg uncertainty relations. On the contrary, if you take Tsallis is extremizing Tsallis entropy. So, extremizer of Tsallis entropy, if you would like to apply maximal entropy principle, then you would find out that this object, if you extremize it based on those two constraints, allows you to get directly to the so-called Tsallis distribution. That's the one which you obtain. And once you have it, the reason why I'm looking for a maximizer of coherent state is because once you find it, you can immediately follow the same procedure as in conventional quantum mechanics and find out the entropic uncertainty relations. So entropic uncertainty relations in conventional quantum mechanics can be found in the following way. So conventional quantum mechanics means that I have Heisenberg uncertainty relations and conventional canonical commutation relations. If I go to a momentum basis, then I get this particular representation of operators for position of momenta. Their eigenstates are just plane waves, which means that if I take any state in position representation, that state is related with its state in momentum representation via Fourier transform. So there are always Fourier duals. And there exists in mathematics a lot of beautiful inequalities that are connecting Fourier duals, or even Pontryagin duals, which means that you integrate over group manifold. And one of those fascinating inequalities is known as a Beckner-Babenko inequality, which allows you to basically put into contact norms of those two Fourier duals and evaluate them in this form. I will actually, on the next transparency, I will explicitly show what this object is. This object is called entropy power, Shannon entropy-based entropy power, and it is optically the same form as Heisenberg uncertainty relations. And indeed, if I would have states that are Gaussian states, then I would get conventional Heisenberg saturation for coherent states. So what the entropy powers are actually. Entropy power for Shannon entropy is defined in a very intuitive way. This is Shannon entropy, this is probability density function. Entropy power is defined as a variance of a would-be Gaussian distribution with unit variance or covariance matrix that would have the same information, Shannon information content, as a given random variable in question. So this is basically the definition of entropy power, which was introduced by Shannon in order to set up various coding theorems he needed to prove. And if you solve this equation, you get a relation that entropy power is just an exponent of shallow entropy. This is basically analog of famous Boltzmann-Einstein relation between number of states and entropy. So important also, if you look on this relation is basically explained in terms of exponent of shallow entropies or conjugate state. So above uncertain relation, this one, is saturated if and only if I have Gaussian states. So it's actually valid only if I have states which have a continuous spectrum, which in my case is true for negative betas. Will be true for negative betas in this case, it's not the issue. And it also highlights the fundamental key role that Shannon entropy plays in quantum mechanics. In fact, if you go to current quantum information theory, quantum optics, you see that Shannon entropy is everywhere. It's precisely because Shannon entropy plays such a fundamental role in setting the uncertainty relations. It's actually even more important than Heisenberg uncertainty relation itself, because it basically constrains also higher correlations, not just variances. But that's a different story. So I can follow the same pattern if I go to generalized uncertainty principle. Again, here is commutation relation. Here are corresponding operators. Now, the corresponding eigenstates are not anymore plane waves. They are more complicated. They are not even square integrable like plane waves. They do not belong to Hilbert space like plane waves. They belong to generalized space of Schwartz, space of Schwartz temperature distribution, similarly like plane waves. For beta negative, the operator self-adjoint and continuum spectrum. And similarly before, I can find a dictionary between position space and momentum space wave state vectors. Now, however, they are not connected to Fourier transform, but they are connected to something more complicated, which is called Abel transform. Again, you can find a lot of mathematical inequalities related to Abel transform duals. They are very useful precisely because now I will prove similar inequality as before, but now for Tsallis entropy power. Again, Tsallis entropy power will be defined as a variance of would-be not Tsallis distribution with unit covariance matrix and zero mean. And it's the same Tsallis information content as the original random variable in question. You can again solve this equation. And the Tsallis entropy power is just exponent, it's proportional to exponent of Tsallis entropy. Again, if you use inequality that we use actually on paper, you prove this beautiful inequality again, entirely in terms of Tsallis entropy. It is again the form which looks very much like Heisenberg uncertainty relation, but now has index Q, which quantifies order Tsallis entropy. But it has this irreducible lower bound, again, as the Heisenberg uncertainty relation. Important point is that it's again saturated if and only you have generalized uncertainty principle coherent states. It's true only for negative beta. It again highlights particular role that Tsallis entropy should play in the semi-classical regime of GUP-driven quantum mechanics. So if you would be really able to identify the GUP-driven quantum mechanics and would be interested in its semi-classical regime, Tsallis entropy rather than Shannon entropy would be the key to work with. I remind you that because coherent states at the same time describe the quasi-classical regime, one can really set up thermodynamics on the same lines as you do in conventional, let's say, thermodynamics. You know, if you take Shannon entropy and insert in Shannon entropy its maximal distribution, you get thermodynamical entropy, which is called Clausius entropy. That's the conventional way how we even arrive at Clausius entropy. So you can do the same here. You can take coherent state, plug it into Tsallis entropy, and you get something which is called Tsallis thermostatistics. So it's basically basically thermodynamics, which is based on Tsallis entropy. So if you would like to describe the borderline between classical and quantum physics, the semi-classical regime, it's a very natural to work in the framework of Tsallis thermostatistics. So, of course, the question is now, what can we say out of this? Does it have any predictions that would be interesting? And one interesting prediction is that one can say something about modification of Newton's law in the GUP-driven universe if you would be interested in semi-classical regime of the quantum gravity. And in our case, we assume that beta is negative, which we shall see shortly. It's a quite interesting cosmologically relevant parameter. And a very natural way how to do that is through Verlinde's idea that gravity is entropy-driven phenomenon. So now I have entropy to, of course, generalize. It's not shallow. So if I know couple Verlinde's idea with non-extensive thermostatistic shallow Tsallis, question is what modification to Newton's law I can expect. So I will just briefly, very briefly outline Verlinde's paradigm. That's much more sophisticated version. This is really very trivial. It's based on the fact that you have some fundamental degrees of freedom you don't have control over. If you take any point in space, you would like to describe physics around that point, you are living in the world of emergent degrees of freedom, and you infer something about that region you would like to describe only from the behavior of the bits or information that is stored on so-called holographic screen, which is around that region you are interested in. So you are deducing your emergent physics from reading information or inferring information from the screen. So if the screen is just sphere, which is not necessary, but it's quite convenient to consider, of this radius, then you can find, you can use the entropic force, which is defined in this way. So if you move a little bit, increase a little bit the sphere, so you increase entropy. The entropic force is defined in a conventional way, like in thermodynamics. And Verlinde showed that standard Newton's law, non-relativistic Newton's law, you obtain if you take this delta x being Compton wavelength, which is the smallest distance on which you can still speak in terms of single particle picture. If you now take that the mass or energy inside of the sphere scales with number of bits on the holographic screen following the equipartition theorem, if you now take the holographic prescription that the number of bits scale with area, and if you take Landau erasure principle, that if you erase one bit of information, then you release into environment heat, Kb, temperature, then basically you get automatically just taking those things together, you get Newton's force. So in our case, we infuse only two things with Tsallis thermostatistics. One is that the heat one form, it's not this one, but in Tsallis thermostatistics has this form, which ensures, among others, for example, that Lejeune transform structure is satisfied. And the Landau principle has generalization, which takes into account that Q is different from 1. And now if I take some dimensionless parameter, like for example, characteristic scale, like this radius divided by Planck scale, then Hawking-Bekenstein entropy on the screen scales with the area, or precisely with this dimensionless parameter. So the number of states I have at my disposal is given from this relation as an exponent to area. And the function phi is some function that weakly depends on L. So if you are now looking on the screen, then from the screen you can deduce that your screen, holographic screen, carries so much bits of Tsallis entropy. So here is the number of states, so this is the Tsallis entropy. So this is written explicitly. So this is Tsallis entropy, which describes the information content of the holographic screen. Now you can use the prescription for holographic force, and you can perform something which is in thermodynamics called Hill's expansion. So first of all, I expand around Q close to 1, and then I use Hill's expansion, which is expansion in L. I get force, and I get potential. It's quite fascinating that this potential it's known as a Mannheim-Casanas potential for spherical symmetric solutions, Schwarzschild-like solutions in conformal gravity. In fact, this term R square is not even there because it's a solution of the sourceless theory. So basically, you have only those two terms. This is very famous potential because it can describe rotational curves of many galaxies, more than 200 galaxies, without any fitting parameter, apart from mass to light galactic ratio. And important is that this parameter here is inverse proportional to Hubble radius. I just will skip other things, if you would like to ask me, you can. We did some phenomenology which is in the paper, but I will skip most of the phenomenology. I just mentioned in summary 4 points. So first of all, we saw that momentum coherent states for generalized uncertainty principle is Tsallis permanent amplitude. with the non-extensivity parameter Q, which must be in this region, which ensures that first and second moments are finite. Then entropy uncertainty relations that are induced by such generalized uncertainty principle basically offer very natural theoretical setup for Tsallis entropy, a maneuvering space for Tsallis entropy. Tsallis entropy is always a question looking for answer. So this is the answer. This is one of the frameworks when it can be used. And in addition, if one applies the maximum prescription and couple maximal entropy distribution with the entropy itself, you get automatically Tsallis thermostatistics, which is a natural framework for discussing the semi-classical regime of quantum gravity, and you can hence look for modification of Newton gravity, and very natural way how we can do it. It's through Fermi-this paradigm. So in order to put some numbers, if you semi-classical regime typically by cosmologists is put at the very end of the inflation, or at the very beginning of a heating period. So if you put numbers, then for example you get that eta time, which is 10 to minus 33 seconds. The Hubble radius is roughly 10 to minus 28 meters, which basically gives you that the difference between 1 and Q, which is 1 meter, it's such a small number that we are basically very close to 1, so very close to shallow entropy, but still not there. Which gives you that the beta, the deformation parameter, must be of order 10 to minus 2, 10 to minus 3, which is basically something that is predicted by string theorists already something like 25 years ago. So it's, we have many more chronological results, but this is, I think, that's sufficient at the moment. So that's all.
Time for questions. I see one at the very end.
Oh, hi Petr, very nice talk. Actually, just a curiosity, it was pointed out by Sabine Senfeld, for example, that the Berlin entropic force approach is basically equivalent to the Newton law, in the sense that you can start as you did from the entropic force and derive the Newton law, but you can go on the other way around and record that it are completely equivalent. The case of general relativity is more complicated and debated.
I would agree. Like, actually, I must say that if you read Ferdinand's paper, this is basically, this derivation is on third page of his paper.
Yeah, sure. No, I want to.
Pages, and he derives completely general relativity, including.
No, I know, but that is more controversial. There are Visser and others that claim that maybe it's not so simple. But for Newton, I think it's not so controversial. I wanted to ask you if you checked also in this modified formulation with modified Newton, if they are equivalent. You went from the entropic force to the modified Newton, so you get man 9,
I don't know how to go,
but not on the other way around.
No, I did not. I don't know precisely what you mean. Go back from modified Newton.
From the modified law, you can define entropy, you can define temperature, and so on in a way that
I did not. And maybe I would like to see it because I didn't know that that's something that people were thinking about.
Any more questions?
Thank you. Nice talk. Just a curiosity also. How much important or how much crucial is that your state must be coherent?
Maybe.
How much important or crucial is that your state should be coherent?
Correlate.
Coherent.
It's very important. I mean, first of all this business is about coherent states. So I would like to describe semi-classical regime. Semi-classical regime is described almost by definition by coherent. In fact, John Clauber invented coherent state path integral precisely because he wanted to describe physics close to classical domain. This is actually still one of the par excellence tools that is used by theorists in the semi-classical domain. So coherent states are really very powerful for description of it. And in addition, we still have not well understanding, not good understanding how to go from classical to quantum physics. So coherent states are wonderful tool to explore this region. And in addition, because they saturate uncertainty ratio, then of course they are as close as possible classical as quantum mechanics allows you in this respect. It's very natural to explore.
Okay, so let's thank the speaker.